Well, thank you very much, Linda, and thank you for the kind words and the invitation to be here. It's an honor to be here. This paper, I'll put up my co-authors' names in a moment, but this paper is on diagnostics for respondent-driven sampling, and the full citation is a little bit later in the talk. So I want to mention that this work is part of broader work on respondent-driven sampling and other methods for sampling hard-to-reach human populations. This is a list of my co-authors, and in particular on this paper, Matt Salganik, who's a sociologist at Princeton, and Lisa Johnston, who's an epidemiologist affiliated with a couple of other universities, are co-authors. And I'll mention some other work where Mark Hancock is a co-author and a couple of others. But having this cross-disciplinary team, as I was just speaking with Linda, was quite an advantage for getting a broad perspective on this topic. So a brief outline of the presentation. I'll talk about link tracing population sampling, hidden population sampling in general, respondent-driven sampling as a particular variant thereof. I'll talk about, very briefly, how we make inference from respondent-driven sampling samples, and this inference inherently requires quite a number of assumptions that I'll spend a little bit of time on. And then the meat of this paper is about diagnostics that are related to those assumptions. So we'll talk some in detail about some diagnostics, and then we'll talk about an application and have a brief discussion. So the idea is that you have a human population that's very hard to sample. So you can think about people like injecting drug users, men who have sex with men, and sex workers. How do you sample them? UNAIDS actually requires information about these subpopulations for estimating HIV prevalence in most of the countries in the world. And one of the commonalities of these populations, besides being hard to reach, is that they're very often connected by an underlying network of social ties. So we could imagine doing something like a traditional survey sample where we have some sampling frame and we do some probability sample on the frame, and then we use some sort of sampling weights to analyze the data. But when we think about populations like these, there's really no practical sampling frame, and so we need to do something else. So if we have a population that's joined by a social network of relations, and if the researchers can access some of the members of that population, then what we can do is we can use link tracing network sampling. We begin with a reachable, usually convenient sample of members of the population who we call seeds, and then expand the sample by following ties within the social network. And this is link tracing network sampling in general. Now, respondent-driven sampling, which is the topic of this paper, is a particular form of link tracing network sampling. In particular, it deals with the issue of dependence on the initial convenience sample by following only a small number of links from each person in the sample. So if I have 100 friends and I'm sampled and then all 100 of my friends are sampled, now I've spent a sampling budget of 101 and I've only made it one step beyond myself. If I only sample 2 of my contacts and then 2 of each of their contacts, the sample gets much farther away from this convenience sample. And so this is the first clever innovation of respondent-driven sampling. It was introduced by Doug Heckathorn in 1997. Secondly, we have an advantage of confidentiality. So respondent-driven sampling is a particular variant where sampling decisions are actually made by the participants themselves. So rather than asking you to name everybody you know who injects drugs, which might be problematic for confidentiality reasons, I give you 2 coupons and I say, give these to people who you know who inject drugs and tell them to participate in the study. So statistically, you might imagine this presents problems, some of which we'll talk about later. How am I making those choices, and is it in the way that a researcher might want? But practically, it really makes this method possible in many of these populations that are stigmatized. And finally, I'll mention that because the final sample really depends on the network, we need to make sure our inference respects the network structure in some way. And there are various ways to do that, and I'll mention those briefly, although they're not the subject of the primary paper under discussion here. So this method has been used in hundreds of studies actually at this point in dozens of countries around the world. And it's used for lots of national estimates of HIV prevalence, which are also used to make funding decisions about things like HIV interventions. And it's incredibly effective at collecting large and relatively diverse samples in many populations. So the people in the field are very convinced this is a really valuable sampling method because it gets them information about these populations that are hard to understand. And then it falls to the statisticians to decide what to do with the data. So just a picture to give you a sense of the sampling method. We can imagine that this is a population of interest, and if we're interested in HIV status, the red dots can represent HIV positive people, the blue dots are HIV negative, and they're connected by an underlying social network of ties that you can see. So if I'm sampling this, I might start with some convenient sample of seeds. Here, 2 of them happen to be infected, and visually I'll move that circle into the middle. And I imagine that I give each of these people 2 coupons, which they then pass to others they know in the population, and the sample expands. And then they pass on coupons, and then they pass on coupons, et cetera, until the sampling stops when I reach my desired sample size. I can overlay the unsampled nodes on the sample, and you can see that we've reached some part of this underlying population. Now, while I have this slide up, I want to introduce a couple of pieces of terminology I'll use later. One is the degree. So the degree in a network is the number of ties of a node in the network. So each node has a given degree, and this guy up here with 2 ties has degree 2. And the other notion is the notion of homophily. Homophily is the tendency for like to be tied with like. And this is what I've written up here is one parameterization that I don't want you to get hung up on. But the notion is that we might think about a social network as not being homogeneously connected, but that there might be more ties within different groups rather than across groups based on various characteristics of interest. So I mentioned the characteristics of respondent-driven sampling before, and I want to mention statistically some of the challenges posed by respondent-driven sampling and also link tracing network sampling more broadly. So first, the sampling does depend on the network, but you might imagine from the data structure that we get to see, we actually don't get to see the network. We might get to see a trace through the network, but that's all we get to see. Secondly, we end up with the initial sample selected by some sort of a convenience mechanism. And the final sample really depends very heavily on that initial sample that was selected in this convenience way. And finally, I mentioned we didn't know a sampling frame, but we might not even know the size of the underlying population. So these challenges are present in almost all forms of link tracing network sampling in hard-to-reach human populations, and respondent-driven sampling is no exception. And I just want to mention as a statistician that there are actually there's been a great deal of work in statistics over the years on inference from link tracing network samples. And that work varies very much in its fundamental assumptions and also how to make inference. So although many of these sampling designs have a lot in common, there's no consensus on how you would make inference from data that have these challenges. We're going to talk about the assumptions of a method based on a very common inferential approach, both in respondent-driven sampling and in survey sampling more generally, is something like a ratio estimator or a generalized Horvitz-Thompson estimator, where the notion is we want to estimate a population proportion, like the proportion infected. We have some sort of a variate that we observe on all the sampled units that here is a binary indicator of infected or not uninfected. And we have a sampling indicator, which is a random variable in this context. And then we end up with an estimator of this form where the numerator is an unbiased estimator of the number of infected individuals in the population. The denominator is an unbiased estimator of the number of individuals in the population. And provided that these pi i's are actually the probabilities of each of the sampled units occurring in the sample, this estimator is approximately unbiased for the population mean. Now, the key point here is that it does require knowing these probabilities. And so with respondent-driven sampling, we're faced with the task of how we can know or try to know these probabilities. And that's what we try to do here, and I'll mention the most common assumption that's used to estimate these probabilities, and I'll very briefly mention some other work that makes other assumptions. But the key point is we're trying to get to this in order to make inference. So the most common approach to creating a model for respondent-driven sampling is to think about a random walk on the space of nodes in the underlying network. So if we have a network that's fully connected and undirected, and we have a random walk on the space of the node, so we start at one node, we move to an adjacent node, etc., completely at random, then we end up with a system that we can think of as a Markov chain on the space of the nodes in the network. And it turns out the stationary distribution of that Markov chain is proportional to nodal degree. So we let this chain run for a very long time, and a node, somebody with 10 friends is twice as likely to be sampled as somebody with 5 friends. So if we approximate the link tracing sampling process in respondent-driven sampling by this Markov chain, and we assume that the sample can be treated as coming from the stationary distribution, then we can consider the sampling probabilities to be proportional to the degree. And this is the approximation used in these two quite fundamental papers by Doug Heckathorn and his colleagues, including my co-author on this paper, but 10 years ago. And so we end up with an estimator where we inverse probability weight by nodal degrees. So we ask people how many contacts they have in the target population. We trust that that number is true. And then here we use the degree rather in the place of the sampling probability in this formula. And because the constant of proportionality cancels in the numerator and the denominator, we again have an estimator which under these assumptions is approximately unbiased. So in order to do this, we need to make a number of assumptions. I'll ask you to look at the blue part of the table to begin with. And these are the assumptions of the estimator on the previous slide, which is due to Volz and Heckathorn. So first of all, we need this random walk model to be approximately true. And one of the key things is that we need, the random walk model assumes that sampling is with replacement, whereas in practice, sampling is typically without replacement. So we need the population size to be considerably larger than the sample size in such a way that it allows this approximation to be reasonable. The random walk model also assumes we have a single non-branching chain. And so the more branching there is in the sampling, the farther we're going to deviate from this random walk model. Once we have a random walk, we also need to make sure our random walk is long enough to remove the dependence on the initial sample. So one thing that we need is to sample sufficiently many waves from the original sample to get away from the original sample. We also need the homophily to be weak enough. So that is to say, if infected people only ever talk to other infected people, I can have an extremely long sample chain and still have a very high dependence on the initial sample. So the appropriate number of waves is going to depend on the level of homophily or clustering in the network. I also need the graph to be connected. You can think about a disconnected graph where people in neighborhood A never talk to people in neighborhood B as an extreme form of homophily on neighborhood. And you can imagine that in that case, if you start with a sample in neighborhood A, you're never going to sample from neighborhood B. Once we've done all this and we have an approximate random walk that's approximately mixing within the population, we then need to be able to estimate the sampling probabilities, and we need our estimates of those to be valid. So for that, we first need all the ties to be reciprocated. Remember, we needed an undirected network for this random walk approximation. We need people to accurately report their number of contacts in the underlying population. And we need people to pass coupons at random among their contacts in the target population. So these are quite challenging assumptions, and a fair amount of my work, largely outside of the paper currently under study as a statistician, is to try to develop alternate inferential methods that allow us to relax or change some of these assumptions. And one of the reasons I must say that I wanted to work on the paper that I'm currently presenting is because I wanted to know as a statistician what the next important questions are. Which of these, all of these assumptions can be quite severe, but which of them are the most important? And so one way to think about which of them are the most important is to look at actual data and look for evidence of these issues in actual data. So that's what we've done in this paper. So just to mention, I'll mention just a couple other papers quickly and just show that, in this paper, I remove the finite population assumption, and I assume the population size is known, and I'm able to make finite population adjustments. And then in this other paper, we show, which is also forthcoming in the JRSSA, in this other paper, we actually look at in this other paper, we relax some of the assumptions about seed dependence, and we instead do the inference based on fitting a network model and conditional on the initial seed's characteristics. So I don't want you to think that these assumptions are fixed. The idea is that we as statisticians can make the assumptions, we can change the assumptions within obviously some parameters, and that's one of the reasons I find the material in this paper interesting. But we're going to focus on these original assumptions of the Voltaire-Cauthorne estimator today. The paper actually addresses a few more of the assumptions that I'm going to talk about in the talk today, but I'm going to talk about the assumptions in blue today and show some diagnostics for them. In particular, here are the assumptions that I'll focus on. With respect to the finite population, we want to know if the sample fraction is large enough that we should be concerned about violations of the infinite population assumption or the with replacement assumption. We want to know if the final sample has gotten far enough away from the initial sample to be relatively independent. We want to know if our estimates are sensitive to self-reported degrees. We want to know whether different groups might be better at recruiting than other groups, thereby biasing the recruitment into the sample. And we also want to know if some group is more likely to be sampled than another. So this is the paper. This is the paper under discussion today. It's called Diagnostics for Respondent-Driven Sampling, and it's forthcoming in the Society's Journal. So what we did was we had 12 studies in the Dominican Republic. There were 4 cities, and in each city we looked at men who have sex with men, drug users, and female sex workers. The sample sizes of these studies varied from 300 to 500, and we used information both in the respondents' responses to these surveys, in the meta-information about when they came in to do surveys, the timing of the surveys, the number of coupons they returned, and things like this. And also in a follow-up survey that we administered to participants who returned to the study site to receive secondary incentives or HIV test results or things like this. So we actually saw about half of these people twice, and we got that information. So we were able to capture additional information on them. And in the paper, we detail a number of additional questions we asked and pieces of data and information we recommend practitioners find if they're interested in using these diagnostics. So first we'll look at finite population effects. So I mentioned that I had another paper introducing a method of adjustment for finite population effects. And so what we did with respect to the finite population effects is we just looked at the difference between the successive sampling estimator and the Voltaire-Cauthorne estimator. And then if that difference was large, then we decided, well, okay, maybe we should be really concerned about whether we have substantial finite population effects here or not. This is a histogram of the differences over the 12 sites. And I think it's just the prevalence of, I think it's HIV. But you can see that the difference between these estimates is quite small. And so what we concluded is in most cases in these populations, within a reasonable range of population sizes, we didn't have substantially large finite population effects, which is reassuring. And you might have also noted that I mentioned before that this estimator correcting for finite population effects required knowing the population size. So in this paper we also describe how we've used another method to estimate population sizes, and we used a lower bound, like a worst case scenario, a lower bound from the highest posterior density region from this population size estimate in this sensitivity analysis. If we had seen a problem here, a possible remedy for this problem is that, thankfully, people in this room, like on the stage, have introduced an estimator that adjusts for this if that's necessary. Okay, the next, and I think this is perhaps one of the most critical questions in respondent-driven sampling, and luckily one of the things that we can get a handle on with a number of diagnostics, is the bias introduced by the initial sample. So these plots show a time trend in the estimate as additional people are recruited into the sample. So you can't really read this axis, but it starts at 1 and it goes to 300. And the idea is we computed the estimate when there was only one person in the sample, and what do you know? The estimate was 1. So 100% of the people were infected, which we take with a grain of salt. And then we computed again with 2 people and 3 and etc. And the idea is the one on the left here, which is drug users in Barahona and the question of whether they had engaged in risky sex behaviors in the last 6 months. And you can see this one seems relatively well behaved. After about halfway into the sample, the estimate sort of stabilizes and you feel like, okay, we've gotten away from whatever transient phase was introduced by the initial sample, and we've gotten to a place where all of the chains in the sample might be mixing quite well, and we've captured an estimate of this prevalence that's reasonable. Now the one on the right looks less nice. You can see that it just continues to increase over time in the sample, and you're left to wonder if you were to continue this sample indefinitely, would this estimate continue to rise, in which case we might not feel very confident in the estimate on the right. Now, one of the very interesting things to think about in this particular example is that both of these plots are for the same population. They're just for different behaviors. So that says that this sort of seed dependence and convergence, it may be different for different characteristics within the same population, but we think that these plots are really interesting to look at, to assess your level of confidence in the estimates you get. We can also look at similar plots that break down the estimates by the different chains in the sample, starting with different initial nodes. And you can see here that these different chains in the sample seem to be tapping different subpopulations, which you wouldn't have seen if you just looked at the time trend. These are the same variable. The time trend, it looks quite stable, but here it shows that maybe we have different subpopulations we're sampling. Here's another case where we see the different subpopulations, and we can add yet another plot where we see that over time in the sample, each of these lines is a different chain that's initiated by a different seed. The red lines represent infected people. Actually, they're heterosexual, men who identify as heterosexual within the men who have sex with men community in Higui. And you see that there are a spattering of them in these other chains, but this one chain seems to have tapped into lots of men identifying as heterosexual quite late in the sample, and that accounts for this characteristic over here. I'm going to talk about this one briefly. I'm sorry about the overwriting of the text. I mentioned that we have to assume that people have accurately recorded their number of ties. Well, because we saw these people twice, we could actually take 2 measures of the same thing, and we estimated the prevalence of 4 different diseases based on these. So if you can see that in each pair of dots, one dot is with the earlier surveys, degree estimates, and the second dot is with the later surveys. And the results of this are sort of mixed for practitioners. The difference between these dots tends to be within the margins of errors of the estimators, but in practical terms, this represents a difference in about 5% in the HIV prevalence in this particular city, in this particular population. So although statistically they're within the uncertainty we would expect, practically these might have very big practical implications. And I'll just mention I'm working with the student Isabel Beaudry on some methods to deal with measurement error and degrees in respondent-driven sampling. I mentioned that we might have differential recruitment effectiveness. The idea is that here we've taken HIV positive and HIV negative individuals, and we've looked at the average number of recruitments by people of each category, and these are the 12 different studies, and we've computed a ratio of these average number of recruitments for each. So you can see that for most of them, the rates of recruitment of the two different subgroups are about the same, but then we have a few sites where we might be really concerned. This is female sex workers in Igui, and it seems that HIV-negative people recruited about twice as often as HIV-positive people. So if this is going on and there's a level of homophily on HIV status, then it's really important to use an estimation strategy that's not affected by this. So there's several estimators, including some ongoing work with Miles Ott. This is the Salganic Heckathorn estimator and the model-assisted estimator that can adjust for this, but you need to know that it's going on to do so. And I think this is the last diagnostic I'll describe in detail. We also might think that coupons are passed out in a biased manner. One of the issues we were worried about with drug users was employment status. We were worried that if people were employed and had an income and a job and a place to go, they would be less likely to participate in a study for some small amount of money that took some amount of their time. So we asked people who participated in the study what % of their contacts were employed. We looked at the coupons that were distributed, and we asked people, of the 3 people you gave your coupons to, was the first person employed, was the second person employed, was the third person employed? And finally, we asked the respondents who actually participated in the study, are you employed? And in each of the 4 sites, we plotted the proportion employed, and these are sort of looking at the relevant population so they're comparable. We looked at the proportion who were employed. And what we found was sort of the opposite of what we expected. There seemed to be systematically more coupon recipients who are employed than contacts, and also more recruits who actually participated who were employed than people who got coupons. So there are 2 things that could be going on here. The first one is that we've actually talked to people in the field who say, well, I want to give the coupon to somebody who's reliable so they'll actually show up for the study. But the other thing that could be going on here is a level of desirability bias that could be increased the closer you get to the person you're actually surveying. That could account for some of these differences. So it remains an open question to figure out how to estimate these, or how to measure these different levels of referral bias appropriately and without bias. But if those data are available, then we can also find ways, like using a model-assisted estimator, to adjust for them. And they could be critically important in determining the composition of the sample. I'm going to skip this for a moment, and I'll just have a minute or 2 of brief discussion. So respondent-driven sampling is indeed widely used, and it relies on many underlying assumptions. The ones that I listed on the slide, you may be able to think of others, and we can talk about them after the talk as well. There are no definitive tests of these, and indeed our paper doesn't provide definitive tests too. We provide some heuristic tests, but this is an open area of statistical research is to extend some of the work in this paper and come up with more definitive tests, which is really hard to do in this setting where we don't have a strong foundation for rigorous inference. So I'd be interested in talking with others after the talk about your thoughts on these next steps. And so what we tried to do in this paper is present some visual and intuitive diagnostics that could give people using these methods a sense of what's going on in their data, even if the answers aren't always clear. And finally, in terms of hidden population sampling, I really believe that respondent-driven sampling is useful in giving us information in a setting where it's very hard to get information. But one of the things that you may have noticed is that, well, maybe not in these slides so well, but Respondent-driven sampling really requires many assumptions, and the variance of the resulting estimators can be quite high. So my tendency is to not recommend using respondent-driven sampling if there are feasible alternatives. If there aren't feasible alternatives, then we need to do the best that we can do, and it has been used in many populations in addition to the high-risk ones I mentioned. It's been used in recent immigrants, unregulated workers, Nigerian rioters. And finally, I'll mention that this work is tied in with link tracing more generally and subject to many of the same assumptions, or subject to many of the same challenges as other link tracing network sampling strategies. So with that, I'll say thank you, and I should have highlighted, but the paper in the middle here is the one that the talk is focused on, and the rest of these I've cited somewhere in the talk. Thank you very much.
Sure. Thank you. We're right on time, but I'm going to take a couple of minutes for people to ask questions because I think it's really fascinating stuff. If you want to ask a question, could you please use the microphone because we're filming here. So, thank you.
Hi, Paul Northrop, University College, London. It's a question about the seed dependence.
Yeah.
I think probably touched on it on an earlier slide, but would it be worth considering multiple seeds that are non-random and selected to be widely dispersed? And it might enable you to assess the convergence better, and the negative dependence between the series would give you more precise estimators?
Absolutely. Yeah, it's absolutely advisable to choose the seeds as diversely as possible and to try to capture as many subgroups of the underlying population as possible within the seed group so that you have a hope of getting to them. If the subpopulations are too far divided, though, even the seed selection isn't going to help you because you'll get a bunch of chains that look like this. and then if you really want to combine them, then you need to know something to let you post-stratify or do something else. But absolutely.
So can I ask, does that mean that you need to take more seeds? So the fact that you've got so much dispersion there, because, I mean, overall you'll take an average of some kind. Is that...
See, the thing is, if you end up with, you see how there are these three long chains, and they seems like the bottom one is from a very different subpopulation than the top ones. If you took more seeds, imagine that you now have 100 seeds, so say 90 seeds, right? So you end up with 60 that are like the top two and 30 like the bottom one, right? Mm-hmm. Now the average that you would get from averaging across them is largely determined by the composition of your original seeds.
But can you have sort of a continuous sort of distribution rather than subgroups?
Yeah, you absolutely, you could have a continuous distribution. I guess it sort of depends on your assumptions about the structure of the underlying population. What I would rather see is that since each of these is not actually a single chain, it's branching, right? I'd rather see each of these three chains run out even longer to the point where they allow better mixing within the subpopulation. So whatever subpopulation here has prevalence about 0.57, and whatever subpopulation has prevalence about 0.8, I would rather that these chains get to a point where they're both sampling, or they're all sampling in a relatively similar manner from the full population rather than from those subpopulations. So I'd rather, it's a fine balance between selecting a number of seeds and then running the chains longer for a given sampling budget. But both are important, and it's a challenge.
Okay.